Okay, so I'm going over the ice skating example of comparative statics. And we're starting with this model which says we're maximizing how interesting our ice skating routine is by minus some beta weight the judges put on the importance of mistakes times the probability of making a mistake during your Olympic ice skating routine. And our choice variable is the number of tricks we put into the routine. So T, tricks, is our choice variable. Tricks influences how interesting our routine is, but tricks also influences the number of mistakes that we're likely to make. So there's a trade-off. There's a reason we don't choose an infinite number of tricks in an ice skating routine, and there's a reason we don't choose 0 tricks in an ice skating routine for the Olympics. So how do we approach the comparative statics here? Well, first of all, we want to know which of our exogenous variables, and we have 3 of them, do we want to do comparative statics on? And let's just try mental focus. So we want to know, if we increase our mental focus, how will that change the number of tricks that we put into our routine? And we're going to take our first order conditions, and we only have one first order condition here, which is the derivative of our payoff function with respect to the number of tricks. And that we don't know what this function is, so we just say it's the derivative of the interestingness function with respect to the number of tricks, minus beta, that's just a constant, times the derivative of the number of mistakes we make with respect to the number of tricks. And we remind ourselves that the number of mistakes also depends on 3 other things. That's the amount of practice we do, our natural athletic ability, and our mental focus. And because it's a first order condition, that needs to equal 0. So there's really 3 steps to this analysis. In the first stage, actually, the next thing we're going to do is we're going to draw a picture of anytime we see something like this, we're going to draw a picture of that whole function. So let's just draw our pictures over here to this side. So this function, the t, the choice variable, is going to go on the x-axis. So anytime you see something like this, the denominator always goes on the x-axis, the numerator is always going to go on the y-axis. So we have the relationship between number of tricks and how interesting our routine is. And this might look like a classic benefit function. Having 3 tricks makes your routine go from really boring with 0 tricks to pretty interesting, but going from 3 to 6 tricks doesn't add as much interestingness. So there's diminishing marginal returns to each trick you add to the routine. And then our other function we need to draw is this function here. So the t, once again, goes on the x-axis. Whatever's in the denominator in this format of our first order condition goes on the x-axis, and the m, probability of mistakes, goes on the numerator. And this is a negative thing, so our first inclination might be to think, does it have the shape of a cost? In other words, as we increase the number of tricks we add, do we exponentially increase the probability of a mistake? And we probably do. If there's only 1 trick in our routine, there's probably not that big of a chance of a mistake, but as we go from 5 to 6, we really increase the chances that we're going to make a mistake as we do this routine. So we've got classic benefit function, classic cost function, and we have our pictures. We also need to come up with a starting equilibrium, and this just says someone, before we changed our level of focus, maximized this thing, and they solved for t. So there was some optimal level of t, optimal number of tricks, maybe that was 4 tricks, and we're going to call that t old. This was the previous number of tricks before we changed t old, before we changed our level of focus. So our problem's now set up to do comparative statics. I'm going to change colors here. And our first line of our comparative statics says, if we increase f, how will that set this first order condition out of equilibrium? So to do that, we need to find f inside of our first order condition, and there it is. It's inside this function, so we need to be looking at this graph. And a change in an exogenous variable is usually going to rotate the graph. So let's see how the graph is going to rotate. I'll keep this in red. If we increase our level of focus, I would actually think that the probability of mistakes would rotate down. So And that's an intuitive thing. You just have to think through it intellectually. So this is going to be with mental focus, which is F. Mental focus is high, and the top one is mental focus is low. So just as we increase F, our probability of mistakes rotates down. So as it rotates down, we need to figure out now what happens to the actual slope at this particular point T. And we notice that the slope is also going to rotate down, so the slope actually goes down. So that means since this represents the slope at that particular point, this whole part of our first order condition is going to go down. And nothing happens over here. So what that means is we're no longer equaling 0. Since our negative is going down, we're actually going to have a positive first order condition. And that's no good. We know that for maximizing a function, our first order condition really needs to be 0. If it's positive and we're maximizing our objective function, that means we're not choosing the optimal value for t. We're choosing something probably lower, and we need to increase it to get a first order condition of 0. But let's go through the process to figure out how to do that. So our second part of our comparative statics, this is the second row, is how do we counterbalance that? Counterbalance. And if this goes down, there's two different ways we can counterbalance it. We could change t to make this go up. That would counterbalance this thing going down. Or we could make this piece go down. So if both our benefit and cost go down, that could get us back to 0. So these two will counterbalance it and get our first order condition back into equilibrium where we need to be. So that's the second row. And then the third row is how do we change our choice variable to achieve what our second row wants to achieve. So for our third part, we're changing our choice variable, meaning we're moving along this axis. There's no more shifting, no more rotating. We can only go this direction or this direction. So let's do it one term at a time. Let's start with this term, meaning this graph, and we want to know how do we get this term to go down, this meaning the slope of this line, how do we get that to go down? And we can try moving t down. Whoops, that didn't work because our slope went up. So we move that direction, we move out, and our slope actually does go down. So we know that t needs to move out, or t needs to increase. T goes up to achieve this. Now let's do the same thing over here. So we have some slope, which is now right here, and the question is we want our slope to increase. So do we move that t in, or do we move t out to get it to increase? And we see that when we move t out, we get a steeper slope, meaning this whole term has increased. So an increase in t, moving it out, will achieve what we want to achieve, and then we're back in equilibrium. And then our last step is just to check the intuition. So what our model has said is that if we increase the amount of focus that an athlete has, then we should increase the number of tricks in their Olympic routine. Does that intuitively make sense? Yes, it does. And so we're done with comparative static.